In this video, we're going to start describing rotational motion. And in this section, the main idea is angular displacement, angular velocity, and angular acceleration all help to describe angular motion. A few essential questions that we're going to answer. First, what is angular displacement? Second, what is angular velocity? And third, what is average angular acceleration and how is it related to angular velocity? Some review vocabulary will be the term displacement, like we used in kinematics, but now we're going to look at it in a different sense. And some new terminology, or maybe review from some math classes, would be something like radian, angular displacement, angular velocity, and angular acceleration. So let's first talk about angular displacement. So in a circle, we have 360 degrees, or 2 pi radians. And a lot of times we're going to use the radian notation, but we need to be comfortable switching back and forth between radians and degrees. And a degree is 100 or 1/360th of a revolution around the circle, whereas a radian is defined as 1 over 2 pi of a revolution. And actually, 1 radian is defined as the angle in which the radius is equal to the arc length. And that's why we have that 2 pi in there. And you can confirm that trying to look at the radius of a circle and the portion of the circumference and all that. But that's where a radian comes from. Angular displacement, just like displacement linearly in kinematics, is the change in position or the distance that we cover if we're only moving in one direction. As an object rotates, the angular displacement is the change in the angle. And so, just like change in position linearly, we have change in the angle. That's our angular displacement. And to denote this, we use a Greek letter theta, and it represents the angle through which we revolve. The counterclockwise rotation, this is important here, counterclockwise rotation is typically designated as the positive. So rotating in the counterclockwise direction, opening up from the positive x-axis is considered positive, whereas clockwise is considered to be a negative rotation. Just like we would say right is positive when we're moving linearly and left is negative, we make the same denotation here in that counterclockwise is positive, clockwise is negative. For rotation through an angle theta, a point at distance r from the center moves a distance given by the equation x equals r theta. So this is the arc length formula here if you've had it in geo or one of your other math classes. So to find the distance that we move along the curve here, that is r times theta. So this distance along the curve, we can find that by multiplying the radius by the angle through which we rotate. The angular velocity of an object is the angular displacement divided by the time. So just like linear velocity is displacement or change in position over the time, angular velocity is the exact same, but it's just the angular displacement divided by the time. And once again, we use another Greek symbol here called omega, and it's a lowercase omega. It kind of looks like the Wegmans W, okay, but it is the letter omega. And that is delta theta over delta t, meaning the change in the angle over the change in the time. And angular velocity is measured in radians per second, and that's why we have to be comfortable converting from degrees to radians, because radians are important. Radians are a special type of unit in that they're dimensionless, and so our angular speed and our angular velocity and our angular acceleration all need to be measured in radians and radians per second, radius per second squared. And so for an object rotating at an angular velocity omega, at a point, a distance r from the center, meaning the radius from the center of the circular path, has a linear velocity of v equals r omega. So what that means is, say we're looking at the Earth spinning on its axis and it has an angular speed of 7.3 times 10 to the negative fifth radians per second. That means it goes through that many radians every second. Remember, 2 pi radians, or about 6.28 radians, is a full revolution. And so we're going through very little of a revolution. And that makes sense because, remember, it takes a full 24 hours for the Earth to completely rotate about its axis. And if the radius is about 6 million meters, we can find the speed at the equator to be 434 meters per second. So standing on the equator, you are actually moving at 434 meters per second with respect to the axis of rotation of the Earth. Now, we don't feel that. We don't feel like we're moving because everything around us is moving as well. But that's how fast things on the equator are moving. Now, does that change for where we are? Well, yes, it does. We are actually closer to the axis of rotation the farther north you go into the northern hemisphere. So our radius is a little smaller. If our radius is a little smaller, then that means we have a slightly smaller velocity, at least the tangential speed that we have on the surface of the Earth. Finally here, angular acceleration. We define that as the change in the angular velocity. Just like linear acceleration is the change in the velocity over time, angular acceleration is going to be the same thing. We denote that with the Greek letter alpha, and that is the change in the angular velocity over the change in time, and we measure this in radians per second squared. The linear acceleration at a point at some distance r from the axis of rotation of an object that has an angular acceleration of alpha is given by a equal to r alpha. So you'll notice a pattern here. To translate from rotational kinematic properties to linear kinematic properties, we just have to multiply by the radius. So to go from theta to x, multiply by r. To go from omega to v, multiply by r. To go from alpha to a, multiply by r. One other thing that comes into play here that we didn't have in linear kinematics is angular frequency. And this is the number of complete revolutions made by an object in 1 second. And so a lot of times you may hear this, especially when we're talking about like TVs or something like that, or processors in a computer. It's 1.2 gigahertz. That hertz, that's per second. So 1.2 gigahertz, that's 1.2 times 10 to the ninth cycles per second. Now, in what we're going to talk about here, we're going to have an angular frequency, and we have a formula to find the angular frequency, excuse me. And we do that by taking the angular velocity divided by 2 pi. So the angular velocity divided by 2 pi, that will give us how many cycles we have or how many cycles we'll make in 1 second. So to summarize these three quantities in both linear and angular, displacement, we measure that in meters, and we use x to denote displacement. Velocity, we use v, and it's measured in meters per second. And acceleration, we use a, and it's measured in meters per second squared. Those are all the linear kinematic quantities, which we've done before. Now the angular, we switch over and we use theta to describe displacement, omega to describe velocity, and alpha to describe acceleration. And how do they relate to each other? They're off by a factor of r. So to translate from angular back to linear, to go from angular back to linear, we just have to multiply by a factor of r. Hopefully from this video you're able to understand what is angular displacement, velocity, and acceleration, and also have an understanding of these vocabulary terms. Thank you.